Welcome, this is the fourth lesson on sequences. Today we're going to look at geometric sequences, a little bit more practice with those, a little bit more, I should say tomorrow in class. So I just want to review them tonight for you. Remember, they're the ones where you multiply either by a fraction or by a whole number. And then after we get done looking at that, because it's pretty similar to what you've been doing with the arithmetic and you've already messed with it once, I want to look at a new kind of sequence that might just really intrigue some of you guys and gals. I don't mean that in a I don't know, gender way. I say guys meaning all of you. So, okay, so on day 4, here's what we're going to do with geometric sequences. I want to make sure you've all been a little bit sticky on this part. Geometric sequences are exponential functions with limitations. Remember, we don't go backwards on the sequence, we start at 1. And it's really appealing for life practices, and I'll show you one of those here in a minute. But what I'm seeing you guys having trouble with is finding what your common ratio is in these. And I know this one seems pretty obvious, but I just wanted to go over how you can see it a little bit easier. So we've got this sequence. I want you to predict the next one. If you said in your mind 64, bingo, you're right. How did you do it? You said, well, I just multiplied by 2 because that's what's happening. Okay? But what happens if you can't quite spot what's happening? Let's say that I give you 81, 27, 9, 3, 1, and I say, what's the next one? Well, you might stumble a little bit more on that. If you said 1/3, awesome, I love it, but let's look at how we did it. You might look at that and go, oh, you're dividing by 3, especially right there, you can see it right there. But we don't ever write these with divide by 3, so remember, divide by 3 is multiplying by 1/3. Multiplying by 1/3. Now, I know that I've talked to some of you in class to see this, but I know that some of you still just need it on the video to rewind and study a little bit more, is you can find that ratio by looking up above and taking the number on the right and making it as a ratio with the number on the left. 4 over 2 equals 2. 8 over 4 equals 2. 16 over 8 equals 2. You should never be without your ratio in a geometric sequence again. If you do not get the same answer from all numbers as a ratio, the right over the left, then you know that it's not a geometric sequence. So on this one, we would have 27 over 81, reduce it. 9 over 27, reduce it. 3 over 9, reduce it. 1 over 3, no need to reduce. And 1/3 over 1, that's complex fraction. Remember, you flip the bottom and multiply, so it'd be 1/3. So never ever be without the ratio. That's how you find the ratio. Next up, I think you guys have done pretty well in class with the recursive formula. Again, you found in order to find anything, you have to go to the one before it, the previous term, and multiply by that common ratio. And then we also have worked a lot with the explicit formula. And with the explicit formula, we always use the first term, not that you have to in your own formulas, but we always use the first term and then multiply by the common ratio raised to whatever position you're wanting, minus 1. And that will give you the number of times that you're repeating the multiplication. Okay, so next thing that I want you ready for tomorrow. Well, let me just give you a kind of problem like what I might give you. I tell you that the first term is equal to 81, and that the common ratio is equal to 1/3. And I'm asking what's the fourth term. Which would be your best formula to use? If you said explicit, right on, because explicit needs that first term. Why couldn't it be recursive? Well, it could be if you wanted to repeat it out to the third term, but you have to have the third term to find the fourth term with recursive. So here we go. We would just go f of 4 equals f of 1, 81, times 1/3 raised to the 4 minus 1 would be 3. Now, I do not expect that you would need a calculator for this. Let me remind you of exponential properties. When you have a quotient raised to the third, that means it is equal to one to the third over 3 to the third. 1 to the third is 1. 3 to the third is 3 times 3 is 9 times 3 is 27. So you'd have 1 over 27. F of 4 equals 81 times 1 over 27. I would hope that you would say, oh, 9 will go in there 3 times, 9 will go in there 9 times, oh wow, 3 will go in there once, 3 will go in there 3 times, and you find that your fourth term is actually 3 times 1, which is 3. Okay? I want you to be able to come to class and, given a number, be able to give me that. Now, let's say that I give you an explicit formula like I did yesterday. In fact, for some of you, I went ahead and took you into this geometric sequence stuff doing this yesterday. So I'm going to give you explicit, and I want you to come up with recursive. So it is f of n equals 5 times 4 to the n minus 1. Okay? Yeah, it may help you to put that little dot in there to separate, and remember that's my first term. So in recursive, f of n equals, we don't know what the previous term would be, so we just say n minus 1 times our common ratio, so it's 4. Now we also have to specify that f to the first, or the first sequence number, is 5. Okay, so that would be completed. Next thing that we want to look at in class, again, is a real world problem. It's an awesome one. When I was in the jungles of Costa Rica, I had a former student who took me ziplining, and I didn't understand the language that well. Tarzan means bungee jump. And so there were these 2 jungle trees. And attached up high on them was this whole harness thing. I didn't realize that they were pushing me off of a cliff. So I said, yeah, I'll do Tarzan. I won't do a bungee jump. But they literally took me and swung me down like this. Now it did form an explicit function with a restricted domain, because I started at 1 second dropping, 2 seconds dropping, 3 seconds. If you're going to hook up a bungee jump, which I don't recommend that you guys build them until you get a lot of licensing, but in the licensing, in all of that, you do learn how to predict. I thought I was going to die, guys. It's so nice to know. Mathematicians design these things. They predict how far it's going to fall, what the recovery is going to be. Okay? So here's what might happen. Is you might come along a bungee jump and they say, well, you know what? We aren't really quite sure what the what the drop is on this, but we do know, we have measured it, that up here at 2 seconds, 2 seconds in, you're 64 feet off the bottom of the canyon. And then over here at the 5th position, let's just number these or else I'll get confused. A2 is 64, 3, 4, 5, let's say that's 8. 8 feet from the bottom of the floor. I hope it's not going any further because you know what, we're in trouble. Okay, so now we want to come up with knowing what's the footage that we start with and how much are we dropping every time. So we go to our formula. I don't honestly go back to any of the given formulas. I think it through and I know, okay, this is times R, this is times R, this is times R. And I can sort of make up an explicit formula, not really explicit because I'm not starting with the first one, but I just take A2 equals, actually it wouldn't be A2, it would be A5 is equal to A2, because I'm getting to that sequence, times my R value, times 5 minus 2. Remember, we always get this from these two. Okay, so my 5th height was 8 feet. My 2nd height was 64 times my R to the 3rd. Again, I can just solve this out. Don't be afraid of ratios. This is being multiplied, divide each side by 64. So we get 8 over 64 equals R to the 3rd. Reduce that, 8 will go in there once, 8 will go in there 8 times, equals R to the 3rd. And we start breaking 8 down. We find that 2 times 2 times 2 is 8. So we know 1/2 raised to the 3rd equals R to the 3rd. We know that 1/2 is our R. Now, when you're actually designing these, you have to also go into the biomedical reports on how fast can you drop a human being before they black out. I came very close to blacking out. It was super scary. I will not allow you to have contact with the film of it or with my former student if I can help it, because I screamed like a baby. Anyway, back to the problem here. I want you to give me the entire sequence. So now you know that the R value is 1/2. I want the explicit formula. So I am looking for f of n equals, I need that f of 1 value right here, times 1/2 to the n minus 1. Okay, because I'm going to also ask you guys to figure out, okay, if you were to design these swings, you pick out the drop you want, and let's see, is your guy gonna hit the ground? And can you get him stopped before he hits the ground? You don't want any deaths on these things. So here we go. First thing that I would do in trying to find this is I would plug back in the A2. I'm trying to find my A1, so I have A2 equals A1 times 1/2 to the 2 minus 1. So 64 equals A1 times 1/2 to the 1st. Well, that made it really easy. So 64 is equal to half of that first drop. Mathematically, just multiply each side by 2. You'll have it. That wipes out. A1 equals 128 feet above the jungle floor. Now, I think mine was much worse than that. So anyway, personal opinion. Be ready to come to class, play with this a little bit. I do have one other thing that I want to show you, and that is a cool sequence that you might see, and I want you to be able to really handle this well. Let's say it goes like this. I'm going to give you one. say I have 2, 5, 12, 23, 38, and I want you to predict the next number. I'd really like you to pause and just work on this for a minute. Hopefully you can see right away, hey, this is not going to be geometric because 5 over 2 is not equal to 12 over 5, and these ratios all have to be the same. Okay, this is 2.5, and this is 2 2/5. If you look at adding, you have a plus 3, plus 7, plus 11, plus 15, and you might go, I can see a pattern here. Do you all see that pattern? So you might say my next number would be plus 19. Okay, but what if I want you to find the 100th term? Well, because you've seen this pattern, I just want you to write it down. What is it that you're adding here? Plus 4, plus 4, plus 4, plus 4. And here comes the power to it all, guys. This was first level, and if it had been a pattern right there, that would have been your linear function, or arithmetic sequence. Okay? That is first level. I just like to think of that as the first level below the sequence, right here. Now, if that's first level, I would call this second level. When you find the repetitive pattern in the second level, this is so cool. Remember how linear functions are x to the first? This means that we are x to the second. You may not remember as well, x to the second is quadratic function. Now I am not real sure just off the top of my head what kind of a sequence this is called. I just always think of it as quadratic. So please wow me, look it up. Google search it, see if you can find what the sequence is. I'd like to know. You can wow all of us. But it is a quadratic function. Now, I'll give you just a little hint that helps with your power of prediction. Is something that somebody's worked out to help figure these out. 2a is equal to that position. 3a plus b is equal to that, and a plus b plus c is equal to that. Now you're probably saying, what the heck does that mean? Here's the formula. Tn equals a to the n squared plus bn plus c. So I want to know what your rule is for this function so that I can ask you any term number and you can give me what the value will be in that term. Here's how I'd go about that. If you know that 2a equals 4, then you know a equals 2. Now, knowing that a equals 2, we take 3a plus b equals 3. We can plug the 2 in for the a. So we get 3 times 2 plus b equals 3. 6 plus b equals 3. Subtract the 6 from both sides. And we find that b is negative 3. Okay, another bit of information there. That's awesome. Now we take this last equation. A plus b plus c equals 2. And we plug in our a value, 2. Plug in our b value, negative 3. And we're looking for our c value. 2 plus negative 3 is negative 1 plus c equals 2. We'd have to add 1 to get rid of that. And we find that c equals 3. Now we can plug these values in to find any term number we want. We know that our equation is 2n squared plus negative 3n plus 3. Now I would simplify it. I wouldn't have those double signs there, so just write 2n squared minus 3n plus 3. Let's look at the power of this. Now let's check it out. This is 1, 2, 3, 4 terms. It should come out to 23, so let's try it. 4n equals 2, n being 4 squared minus 3 times 4 plus 3. 4 squared is 16 times 2 minus 3 times 4 is 12 plus 3. 32 minus 12 plus 3. 32 is 20 plus 3. Ka-chow! We have the fourth term being 23. And now you're ready for me to say, okay, could you please find the 100th term? Here's what I want in class. If your team can possibly get done with the geometric sequences, which I think you'll be able to fly through this stuff, maybe a little bit of time on your bungee jump activity, but then I want you to play with some quadratic functions, get comfortable with these, and then I'd like you to design a third level cubic function. And you can Google search, you can do whatever you want, but I would love to see a lesson like this showing us the basic formula of how to get our cubic equation. All right? So let's get good stuff on the airwaves out there for now. We'll talk to you later. Bye-bye.